Welcome, seeker of knowledge, to the invisible world of electricity. We begin a journey into direct current or DC circuit analysis. It sounds complex perhaps, but fear not, it's like learning the notes to play a cosmic symphony. Think about your world, your phone, your lights, your car. So many marvels run on electricity. DC is a special kind of electrical flow. It moves in one steady direction, like a great calm river of charge, always onward. Grasping DC circuits opens a door to understanding the very heart of modern technology. It's a fundamental script of our technological age. At the very core of this electric world is something called charge. Imagine tiny elementary particles, far too small for our eyes to ever see directly. These particles carry an electrical charge. Some are positive, some are negative. These are the two fundamental states of charge, like the two poles of a magnet, or two sides of a universal coin, and they obey a simple, elegant rule. Opposite charges pull towards each other. They attract, while charges that are the same push each other away. They repel. This dance of attraction and repulsion is the engine, the unseen force behind all electrical happenings in the cosmos. Now, when these tiny charged particles begin to move, to flow in a coordinated way, we call this current. Picture a bustling highway of these charges streaming through a wire, or think of water molecules flowing together down a stream. This collective movement is electrical current. We measure this flow in units called amperes, often shortened to amps. 1 ampere signifies an enormous number of charges, billions upon billions, passing a single point every single second. This moving charge is what brings our devices to life. It lights up our screens. It spins the motors in our fans. It carries voices across vast distances. It is, in essence, energy in motion. So what makes these charges move? That's where voltage comes in. Voltage is the push, the electrical pressure. It's the force that compels the charges to embark on their journey. Think of a water tower. The higher the water is stored, the greater the pressure at the bottom. Voltage is like that height for electricity. We measure it in volts. More volts mean a stronger push, a greater potential for current to flow, and when current flows due to this voltage, energy is transformed. Power is the rate at which this electrical energy is used or generated, measured in watts. Imagine how brightly a bulb shines. That's a measure of its power. Power depends on both the push, voltage, and the flow, current. In our electric circuits, we need something to provide that initial push, that voltage. These are called voltage sources. A voltage source is designed to provide a nearly constant voltage to whatever circuit is connected to it, within its capabilities, of course. The most familiar example is a battery. A humble battery in your remote control is a voltage source. It maintains its rated voltage, say 1.5 volts, for a good while. It's like a steadfast guardian of electrical potential, promising to deliver a certain amount of push. These sources are the prime movers. They are the engines that initiate the flow of charge in countless circuits. They get the electric dance started. Then there are current sources. These are a bit different. A current source is designed to supply a constant current. It will adjust its voltage output as needed to maintain that specific flow of charge, regardless of what it's connected to. Imagine a very specialized pump, one that guarantees a fixed amount of water flows through it each second, no matter if the pipe it's pumping into is wide or narrow. True ideal current sources are less common in everyday household items, but in the world of electronics they are indispensable. For many specialized applications, they ensure a precise, unwavering stream of charge, a steady hand guiding the current. Now let's explore a truly fundamental law, Ohm's law, named after Georg Ohm, a physicist who unveiled this elegant truth. This law describes the relationship between three key quantities: voltage, the push; current, the flow; and resistance, the opposition to that flow. Resistance is like electrical friction. It hinders the movement of charge. Ohm's law states it simply: voltage, V, equals current I, multiplied by resistance, R. So, V equals sine IXR. This concise equation is a cornerstone. It tells us how these three aspects of electricity are forever intertwined. If you know two, you can find the third. It's a powerful key to unlocking circuit behavior. Let's try to visualize Ohm's law with something familiar. Think of a simple garden hose connected to a tap. The water pressure from the tap, that's like the voltage. The push, the hose itself, especially if it's narrow or has kinks, offers resistance to the water flow. And the amount of water actually squirting out the end of the hose per second, that's like the current. If you open the tap more, increasing the pressure, voltage, more water flows out, current, assuming the hose resistance stays the same. If you squeeze the hose, increasing its resistance, less water flows, current, even if the tap pressure, voltage, remains unchanged. This simple analogy helps us feel the essence of Ohm's great law. Another giant of circuit theory is Gustav Kirchhoff. He gave us two crucial laws. The first is Kirchhoff's current law, or KCL. This law is all about the conservation of charge. It states that at any junction point in a circuit, any node, the total amount of current flowing into that point must exactly equal the total amount of current flowing out of that point. No charge is lost. None is magically created there. Imagine several roads merging at an intersection. The total number of cars entering the intersection in an hour must be equal to the total number of cars leaving it in that same hour. KCL helps us meticulously track the pathways of current. Kirchhoff's second great contribution is Kirchhoff's voltage law, or KVL. This law deals with the conservation of energy in an electrical circuit. It tells us that if you trace any closed loop within a circuit and sum up all the voltage rises from sources like batteries, they must be equal to the sum of all the voltage drops across components like resistors. Imagine you are hiking in a hilly area. If you walk along a path that eventually brings you back to your exact starting point, your net change in elevation must be zero. You went up some, you went down some, but you ended where you began. KVL is the electrical equivalent of this. Energy is conserved in every loop. Let's consider a very fundamental type of circuit, the single node pair circuit. This might sound technical, but the idea is quite straightforward. It's a circuit where all the components are connected between the same 2 points, or nodes. Think of it like a very simple electrical meeting place. There are only 2 main connection points for everything. This means that every component in this arrangement, whether it's a resistor, a lamp, or a source, shares the same voltage across it. This characteristic simplicity makes these circuits relatively easy to analyze. Often, just Ohm's law and KCL are sufficient. They are foundational building blocks for more complex designs. Now let's talk about how components like resistors can be connected. One way is in series. Imagine beads threaded onto a single string one after another. That's like resistors in series. They are connected end to end, forming a single path for the current. The very same current must flow through each resistor in the series chain. There's no other way for it to go. The total resistance of this series combination is quite simple to find. You just add up the individual resistances. R_total equals sign R1 plus R2 plus R3 and so on. A key thing about series circuits, if one component in the series breaks, the entire path is interrupted, and the current stops for all of them. Another way to connect resistors is in parallel. Picture several lanes on a highway, all starting at one point and ending at another. That's analogous to resistors in parallel. When resistors are connected in parallel, their terminals are connected to the same 2 points, nodes. This means that the voltage across each parallel resistor is identical. The total current flowing from the source will split. It divides itself among the available parallel paths. Calculating the total resistance for parallel resistors is a bit more involved. The formula is 1/R_total equals 1/R1 plus 1/R2 plus 1/R3, and so on. Unlike series, if one parallel path breaks, current can still flow through the other paths. When we have resistors in series, something interesting happens with the voltage. This is called voltage division. In a series circuit, the total voltage supplied by the source is divided or distributed among all the resistors in that series chain. Each resistor gets a certain share of the total voltage, and this share is directly proportional to its resistance value. A resistor with a larger resistance value will have a larger voltage drop across it. This principle of voltage division is incredibly useful. It allows engineers to create specific lower voltage levels from a single higher voltage source by carefully choosing resistor values. It's like tapping into different points of a waterfall to get different pressures. Similarly, when resistors are connected in parallel, we observe current division. The total current flowing from the source towards the parallel combination will split and flow through the different parallel branches. Each branch will carry a portion of the total current, and how much current each branch gets is inversely proportional to its resistance. This means a path with lower resistance will attract a larger share of the current, while a path with higher resistance will see less current. Current, much like water flowing downhill, tends to choose the path of least resistance. This current division principle helps us predict how current distributes itself in parallel configurations. For circuits that are more intricate with many loops and nodes, simple applications of Ohm's law might not be enough. We need more systematic, powerful techniques. Two such methods are nodal analysis and mesh analysis. Nodal analysis focuses on Kirchhoff's current law. It helps us find the unknown voltages at various nodes in the circuit. Mesh analysis, on the other hand, uses Kirchhoff's voltage law. It helps us determine the unknown currents flowing in the different closed loops or meshes of the circuit. These methods turn seemingly complex electrical puzzles into a set of solvable algebraic equations. Understanding these principles of DC circuits is vital. It's the bedrock for exploring the vast electrifying universe of electronics. From the smartphone in your hand to the most distant spacecraft exploring the cosmos, the fundamental dance of charge, governed by these elegant laws, remains the same: a truly grand design.